What we are going to do now, let's look at the application of Newton's second law on the motion and the forces system. Those are the typical Newton's second law problem, and we'll see more other examples in the coming recitation class. First, let's look at the characteristic of this type of problem. And we got to remember for now, the net force or the total force on the object of interest that we're studying is not zero anymore. So the object is going to move with some acceleration. The equation is very simple. We'll have the net force, okay, which is sum of the force, is always equal to the product of the mass times the acceleration. Remember, both force and acceleration, they are vectors. And we can also rewrite the equation in another form. So the acceleration is equal to the ratio of the net force and the mass. And again, A and force, they are both vectors. Okay, so for this type problem, what we are going to do, we are going to pay attention to what is given, what is asked. Okay, so I will just categorize the problem into two types. Type 1, the forces are given, and we need to find the motion. So what the motion can be, can we find the acceleration? Can we find the distance? Can we find the time? So any motion problem, which is coming from the kinematics type of problem, if we know the force. The second type is opposite. What we are given? We are given the information about the motion. We are given the distance. We are given the velocity change. We are given the acceleration. Okay, any information about the motion is given. And then we are asked to find the force. So in other words, given the magnitude of the, given the acceleration, we can find the force. Given the force, we can find the acceleration. So those two types of application are very common in Newton's second law application problem. Now, I want to show you two examples. Example number 1 is we are given the information of the force, and we need to find some unknown thing about the motion. So let's look at the problem together. A 1,500 kilogram car is traveling at a speed of 30 meters per second. And when the driver slams on the brakes, so the car is going to stop. We know the coefficient of kinetic friction between the tire and the road is 0.8. We are asked to determine the stopping distance if the car is traveling up the 3 conditions: along a slope, upward, or down a slope, or on a level road. So in one word, what we know? We know the car has an initial velocity, is moving, and then the brake is on. We know the kinetic friction coefficient between the tire and the road, and we want to know how far will the car move until it fully stops. Okay, so 3 questions here. Let's start with the easiest one. So suppose the car is moving on a level road. That's the road case. What I'm going to do, I'm going to draw a free body diagram. What do we have here? We have a level road. Okay, a surface right here. And the car is moving on it. Okay, I just draw a cart here. It's moving to the right with the initial velocity v sub 0 equals 30 meters per second. And then starting from here, brake is on. So therefore, the cart is going to slow down until it is fully stopped here. And this is when final velocity v equals 0 meters per second. And we want to find out how far does it move with that axis when it fully stops. The other information we are given. So we write down what we are given. I know the mass first. So mass equals 1,500 kilogram. And I also know the mu sub k between the tire and the road, mu sub k equals 0.8. Then, okay, what I'm going to do now, I'm going to do the force analysis on the cart. So when the car is moving, I'll put the free body diagram here. How many forces are applied on it? Always we have gravitational force, mg, and we will have a supporting force, the normal force from the ground, the road here, the normal force. What else? Because we are given the kinetic coefficient of friction. So when the car is moving, as we mentioned this morning, we determine this friction force is going to be kinetic friction force, and it is always opposite to the relative motion direction. So that will be Fk. And remember, Fk is always equal to mu sub k times n. Okay, that's the free body diagram. And then what we do, let's figure out. After we know the forces, can we find the net force applied on the car? And then can we find the acceleration? How do we do this? So along the vertical direction, we can know the normal force minus mg is always 0. Then we get normal force equals the weight of the car, m times g. I will keep it simple here. I'll do the substitution later. And then after I know the normal force, I know the kinetic friction force, Fk, is always equal to mu sub k times normal force. And when we look at the free body diagram right here, so we know along, so this will be this 1D motion. So I will put, this will be my x direction pointing to the right, is my positive x direction here. So, see that clearly. So if I know the Fk equals mu k times n, which is mu k times mg, and then when I look at the free body diagram, I found the net force along x direction. The net force equals what? Fk is the only force applied on the x direction. And because it is pointing to the left, I make it be negative. Negative Fk is the net force, and which is negative mu k mg. Net force equals what? Net force equals m times a. So net force equals ma. That's the Newton's second law. But net force equals this number. So from this equation right here, we see m cross out. I can find, oh, acceleration is equal to negative mu k times g. Now we plug number in. Mu k is 0.8, so negative 0.8 times 9.8. We get the acceleration equals negative 7.84 meter per second square. Why it's negative? Because it is moving to the right, but the friction force is pointing to the left. So it has a negative acceleration, negative 7.84 meter per second squared. Now the problem turns into the kinematics problem, what we did in chapter 4. Okay, so what do we have here? We know the initial velocity right here, v sub 0 equals 30 meter per second. Final velocity equals 0 because it fully stops. And then we want to know when it stops here, what is the total distance? What is displacement that the car moves? When what? When, don't forget we have the a here. The acceleration equals negative 7.84 meter per second squared. What formula can relate acceleration, initial velocity, final velocity, and to find out delta x equals what? And recall. So burn our memory back here. And on the formula sheet, we all have final velocity squared equals initial velocity squared plus 2a delta x. This is the formula we can find on the formula sheet. Now let's see. If we use this formula, do we know V? Yes. 0. Do we know V sub 0? Yes. Do we know A? Yes. So delta X will be the only unknown. So now to solve this problem, just plug what we have here into the formula. I have 0 squared, final loss squared equals 30 squared, initial squared, plus 2 times A. A is, don't forget, A is negative 7.84 times the displacement, delta X. Solve the equation. Delta X is the only unknown, so delta X equals, move this term to the left, negative terms in the past equals, so 900 over what? Over 2 times 7.84. And do the calculation, we got delta X is about 57.4 meter. So it tells us if the car is moving on the leveled road, when the brake is on, it has the friction force between the tire and the road. When mu sub k equals 0.8, it will fully stop at the distance of 57.4 meter. Okay, so this is the first question. When it is moving on the leveled road. Now let's look at the second one. So what if, I'll cover right here. So second problem. Okay, let's still move this up here. The second one. The second case is when the cart is moving along a slope up. So what I have here, everything is the same, still in the same initial velocity right here. So the car is moving along a slope. The angle of the slope theta equals 10 degrees. So the car is moving right here. So suppose this is the moment that the brake is on. So then it goes up until it fully stops right here. We want to know how far it moves. And again, this is the velocity v sub 0 equals 30 meters per second along the slope. So suppose this is going this way. All right, this is the moment when the car fully stops and v equals 0 meters per second. Same thought. To figure out what the distance is, so we know initial velocity, we know final velocity. If we are able to find the acceleration, then we'll be able to find the distance. What determines the acceleration is the net force. So what I'm going to do now, I'm going to, put a Cartesian coordinate system and going along the slope is my positive x direction. Zoom it. And this will be my y direction here. Okay, y direction. Then we'll look at any moment. So suppose the starting point here, how many forces are applied on the cart? So we have seen this many times already. This morning, we spent a lot of time on the inclined surface study here. So we have a gravity always pointing downward. And we always have a normal force along y direction. That is a normal force. Because the cart is moving upward. So we have a kinetic friction force pointing downward because it is opposite to the relative motion. This is Fk. All right, so those are the force applied on the cart. And we said, so we always want to look at the net force along x and along y. So we have to decompose the gravity into the y component from here to here. This angle theta, that is theta as well. So then we'll have mg times cosine theta. This is this one. And also we'll have one x component, and this is mg times sine theta. So this small force is a component of mg along x direction. After we have those two forces, we do not need to look at mg anymore. So mg is gone. we have those two components only. Now let's look at, so along y direction, we'll always do the y direction first. Why? Because along y direction, the net force should be 0, which means the normal force minus mg cosine theta equals 0. The car never leaves the ground. Okay, and then we got, okay, the normal force equals mg times cosine theta. Then we'll look at the x direction. So this is the x direction here. What is the net force? The net force, there are two forces. They are both pointing downward. They are both pointing to the negative x direction. Okay, so along the x direction here, what are the net force? So the net force along x direction equals the sum of the two forces, Fk and the component of mg along x. Because they're both pointing the negative direction, they're both negative. So negative Fk plus negative, so minus mg sine theta. That's net force. And always we replace Fk because kinetic friction force Fk is always equal to mu sub k times n. So the net force I continue here equals negative mu sub k times mg cosine theta is Fk, then minus mg sine theta. That's net force. And net force equals m times ax, the acceleration along a direction. Okay, so now let's look at the equation here. I rewrite it as a regular function. So copy the problem right here. I got negative mu k mg cosine theta minus mg times sine theta equals max. And then we'll see m cross out. We'll get the acceleration along x direction. So ax equals what? Equals negative mu k g cosine theta minus j sine theta. Still, they're all symbolic expression. I don't have number. After I got the expression like this, I start to plug number in. So what is mu sub k? Mu sub k equals 0.8. So ax equals negative 0.8 times g 9.8 times what? Cosine 10 degrees. Minus what? Minus 9.8 times sine 10 degrees. Then you can use your calculator. And I did my work already. I found A equals what? A equals, do the calculation, AX equals negative 9.42 meter per second squared. Then we'll have the same way. So after we got the acceleration along x direction, and plug v squared equals v sub 0 squared plus 2a delta x. That's the formula we have. Then we got v sub 0 equals 30. Final v equals 0. 0 squared equals 30 squared plus 2 times a. A is negative 9.42. And then times delta x. Delta x is the only unknown. Move this term to the left. Solve the equation. We got delta x equals what? 30 squared, 900 over 2 times 9.42. We move this to the left. This negative sign disappears. And do the calculation. We got delta x equals 47.8 meter. Okay, so that means if the car is moving upward, when the brake is on, it will move a shorter distance than the leveled road. This is moving up. Okay, so now let's see the third case. Same thing. What if the car is moving downward? Will we get a similar answer or not? So still, this is the same slope right here. The angle is theta. So now, because it is moving down, that will be the initial position. So it goes down here. And at this moment, it has v sub 0 equals 30 meter per second. It goes down. And it goes down, down, down here. When it fully stops, right here, we got V equals 0 meter per second. And then we want to figure out how far it goes along the slope, delta x. So the motion is going that way. So what I'm going to do now, I'm going to still draw the free body diagram, find the net force, find the acceleration, then I can find the displacement. And what I'm going to do now, I'm going to choose because it moves downward. Okay, so I will set up my Cartesian coordinate system. So along the slope moving downward will be my positive x. It's up to you. Okay, you can still make moving upward. It's positive x, but I want to show you my way. So this is negative positive x, and that will be the y direction. Still xy are perpendicular. So that's the Cartesian coordinate system. Then draw the free body diagram. So the car is right here. How many forces are applied on it? Gravitational force, mg. Normal force, perpendicular to the surface, along the y direction. What is the direction of the friction force? Because the car is moving downward along the slope. So between the tire and the road, the force is going to opposite to its direct, the motion. The motion is downward. So the friction force is opposite to it. Fk is actually pointing to this direction. So look at the difference between the downward because it moves up. Friction force is pointing down. Here, because it moves downward, friction force is actually pointing upward. Okay, what do we do now? Find the net force along x direction. And because Fk depends on the n, I still need to know what the normal force is. Same thing, whenever we have those kind of problem, we always decompose the gravity along the y direction. So from here to here, the angle of theta is mg cosine theta. And then from here to here, I have the x component, mg times sine theta. When I have those two components, remember, we do not need to look at the mg anymore. mg is gone. How many forces? 1, 2, 3, 4. Do the force. So along y direction, we have n minus mg cosine theta equals 0. Then we can get normal force always equals mg cosine theta. Nothing new. Still, this is the 5th time already we have seen this analysis along y direction. Then we look at along x direction. So remember, my positive x direction is pointing downward. So look at the force. mg sine theta is along positive x direction. So along x direction, the net force equals what? Equals mg sine theta minus Fk. Okay, because Fk is opposite to the x. It got to be minus. And what is Fk? Fk is always equal to mu k times n. And n is mg cosine theta. I kind of, do a quick substitution. Fk equals mu k n. N is mg cosine theta. And this net force equals ma. Or you can use max. Does not matter. Okay, so look at the equation right here. Net force equals ma. M. It really does not matter what the mass of the car is. It does not affect the acceleration. So ax equals what? Ax equals g sine theta minus mu k g cosine theta. Symbolic expression. Then we plug number n. G is 9.8. Sine theta, sine 10 degrees, minus 0.8 times 9.8 times cosine 10 degrees. And after I do the calculation, I found ax equals what? Negative 6.02 meter per second squared. That's 8. So if you do the calculator, use your calculator, you'll get a negative number. Negative means what? Negative number means the actual acceleration will be along the loop pointing upward. It slows down the car. Then use the same formula right here. Final velocity equals of squared equals initial velocity squared plus 2a delta x, and copy the same formula. I can do the calculation. Delta x equals what? Equals v squared minus v sub 0 squared over 2 times a. So that will be 900 over 2 times 6.02, and which is 74.8 meter. So this last step is the same as what we did before. We use that formula to save time. I do not go the detail with you. So then the car will move along the slope with a distance of about 75 meters. So down the slope, it goes longer. Up the slope, it goes shorter. And on the leveled road, the distance is the brake distance is between. That's, yeah, so we can quickly judge, use the common sense here. It makes sense. So that's the final answer. Delta x equals 74.8 meter down the road, down the slope. That is the first question. Okay, so what we have here, there's a typical problem. We know the forces. So 3 cases here. We know the forces, and we are going to find out the motion. So the displacement is a motion. Okay, typical kinematics problem. Type 1. Type 2. So the other example I have here is a problem. We are given the information of the motion, and then we want to find the force. So quickly read the problem. Okay, zoom, zoom, zoom. On the dog sled race here, 2 ropes. So 2, highlight here, 2 ropes are attached to the sled and 1 on each side of the dog. So the dog is pulling the sled, and the dog has 2 ropes, 1 on each side. We know the sled and the rider together has a mass of 200 kilograms. So we know the total mass of the sled and the rider here. And when the starting gun sounds here, it takes the dog 15 meters to reach their cruising speed of 5 meters per second across the snow. So when the when the dog reaches the cruising speed, so the maximum speed, then it will just keep running in the same speed. The dog runs 15 meters. And then what else we know? We know the rope pull up at a 10-degree angle, the 10 degrees angle. And we also know the coefficient mu sub k equals 0.06. Then we need to find out what is the tension in the rope. Okay, so whenever we are given a problem, try to picture it. Draw a quick graph. It does not have to be perfect. Just draw what we are given on the graph here. So what I have here, there is no slope anymore. The sled is running on a horizontal road here. And let me draw just this. So this represents the rider and the sled. Okay. It is moving along the road. What we have here, we know there are 2 ropes applied on it. So there are 2 ropes. They are both. So there's actually this. When I look at like the front view, I can only see 1 rope. But to make sure we display all the information, I still draw the 2 ropes here. Both of them have the tension T, and they both have the angle that's 10 degrees. Okay, so those 2 tensions applied on the sled from the dog have the same magnitude, the same direction. And then what else? The gravity. Okay, so the sled and the rider has a mass of 200 newtons. So I have mg here, mg, and there is always a normal force perpendicular to the ground pointing upward in this case. Do we see another force? Because the sled is sliding on the snow, we will have a kinetic friction force, and we'll have Fk, which is pointing to the left because it is opposite to the motion of the sled here. Okay, and what I see here, two tensions from the two ropes, one normal force, one gravitational force, one friction force are all the forces applied on the sled. And what we know, and so this is the free body diagram. And then write down what else we know. We know initially the sled, just start from the rest. When the gong sounds, then the dog starts to speed up. So the initial velocity is 0. They start from the rest, 0 meters per second. And it runs delta x equals 15 meters. Then it reaches the final speed, final velocity v equals 5 meters per second. So this, I know initial velocity is 0, final velocity is 5 meters per second, and it runs 15 meters to reach that speed. Those are the information of the motion. Okay, so what I have here is the motion information. Then I want to figure out t, what t is. T is the unknown. How do we solve this problem? I know the sled is going to move with a constant velocity during the speed up process here. And the acceleration depends on the net force along the horizontal direction. This is my x direction here, along the horizontal direction. And what is the acceleration? We step because the motion information is given. Let's see, are we able to find the acceleration from the given information right here? And still think of the formula. We have v squared equals v sub 0 squared plus 2a delta x. This is the formula we can find from our cheat sheet or formula sheet. We know v sub 0, we know delta x. A is the only unknown. So from the information, so given the motion, I could get the acceleration is. So what is the acceleration? Plug number in. I have 5 squared equals 0 squared plus 2a times 15. Solve the equation. We'll get what? So move, okay, 0 squared still 0. The 5 squared, 25. Divided by 30. So a equals 25 over 2 times 15. 25 over 30, 5, 6. And if we return this to the decimal number, it equals 0.833, okay, about meter per second squared. I know the acceleration along the x direction, so I can keep the x here or just keep the a. So write down the a. The acceleration. So leave the a right here. Then we do the force analysis. So we want to know what is the net force applied on the x direction. Because there is a friction force involved, I have to know what the normal force is because mu k is always equal to mu sub k times n. So I start with free body diagram. This is the x, this is the y direction. So along the y direction, do the force analysis. Normal force is the force pointing upward. Pointing downward is what? Is mg. Beside those two, I also have the tension. The tension, part of the tension is pointing upward as well. It has a y component of the tension. So m plus what? Plus t times when we decompose the tension, so the vertical coordinate, the vertical component, so this t, decompose it, what's its y component? T times sine theta. So t times sine theta, because there are two t, double it. So those are the tension points upward along y direction. Then minus what? Minus mg equals 0. Okay, so by solving this problem, what we can get? We can get n equals, move the two term here, mg minus 2t sine theta. Keep the symbolic expression. We'll plug number later. So after we got n, then you can get, okay, then fk equals mu sub k times n equals mu sub k times mg minus 2t sine theta. That's fk. Then we'll look at the x direction. So look at the x direction. How many forces applied along x direction? 2 tensions and friction force. So along x direction, what is the net force? The net force along x direction equals what? Equals t times cosine theta. So this is component from 1t. Double 8. We get the 2 tensions because there are 2 ropes pulling the sled. So 2t cosine theta. That's along part of x. And the fk is pointing to the negative x direction. I will minus fk. That's net force. And net force equals what? Equals m times a. We got a already. So that's the equation we have here. Then we plug fk in here. And what do we have? We have 2t cosine theta minus fk minus mu sub k times mg minus 2t sine theta. Don't forget the parentheses. Just plug this here. Equals ma. Then we look at this equation. What do we know? Do we know t? No, t is the unknown. We know theta. We know mu k. We know mg. We don't know the t, same unknown. We know theta. We know a. We know m. And t is the only unknown. So before I plug a number in, I simplify the expression here. I get a t out. So the quick math here, 2t cosine theta plus negative turns upon 2t mu sub k sine theta and minus mu k mg equals ma. And those 2 terms has t here and you get t out. So that's 2t times cosine theta plus mu k times sine theta equals what? I move this term to the right, equals mu k mg plus ma. Then divide by 2 and the parentheses here, t will be the unknown. So solve for t. T equals mu sub k mg plus ma over what? Over 2 parentheses cosine theta plus mu k times sine theta. Now, until now, you can start to use your calculator. Okay, so you don't need to do the plug number in before. Keep the symbolic expression until the last step. Now we start to plug number in. What is mu k? 0.06 times mg. What is m? 200 times 9.8. And plus, what is m? 200. What is a? We got a from step 1. We got a here. A equals 0.833. So 200 times 0.833 divided by 2 times cosine what? 10 degrees plus mu sub k 0.06 times sine 10 degrees. Now you start to click your calculator. Don't forget, keep the parentheses around the numerator divided by the denominator. And if you do the calculation, the final answer, T equals 142.8 Newton. That's final answer. So the tension in each rope, what are the tensions in the ropes at the start of the race? What the start of race? When the sled is speeding up from 0 meter per second till 5 meter per second speed here during this process. the tension in the rope is equal to 142.8 Newton. Okay, that's the tension in each rope. There are 2 teeth applied on the sled. This is the typical problem. Given the motion, we can find the acceleration. And then write down the force analysis. F net force equals ma. A is known now, and the T is unknown. So for the single unknown, we get the final answer. Okay, so I hope those 2 examples are very, very fundamental thing. Given the motion, find the force. And the problem 1 is given the force, find the motion information, determine the stopping distance. And or you ask, find the acceleration. After we find the acceleration, we can use the kinematics, the formulas to keep working and find some other information about the motion. Okay, so I hope those 2 examples can help you to understand the second law better.